In the last video, we discussed how we can bring together two systems of measurements, MMM and experiments, to create a more causally aware MMM model. We also spoke about the benefits and limitations of this approach. In this video, we are exploring ways in which the primary approach to model building itself could be based on techniques that are essentially built for causal reasoning on observational data, also known as Causal AI. Let us revisit this equation, which we mentioned once in our video about causality, that relates causation to correlation. This was the equation. Causation is equal to correlation plus bias. Here, if we can remove the bias, then correlation can be interpreted as causation. Let us take a simple example to make this idea clearer. Say there are two cohorts of people, cohort A and cohort B. They are all suffering from a particular disease. We want to test the efficacy of a new medicine when it comes to treating this disease. To test this, we administer this medicine to cohort A while giving a placebo to cohort B. Later, we observed that more people in cohort B were cured of the disease than of cohort A. Hence, we concluded that the medicine wasn't really effective. However, while taking a more careful look at both the cohorts, we observed that cohort A constituted mostly of men of age 50 or above, and cohort B were mostly women of age 35 or below. People who were less than 35 could have also received some help from the innate immunity in fighting the disease, and their gender also could have possibly given them some genetic advantages. Here, cohort A and cohort B weren't comparable. That is, they weren't random in statistical sense. That is, this study had bias. How do we address this bias? By making both the cohorts similar. Once both the cohorts have equal or similar composition of age and gender distribution and other relevant factors, we could repeat the experiment and make better and correct causal estimates. This is an example of a controlled trial where we can adopt the technique of randomization to make the cohorts same and thus remove the bias from the equation, making observed correlation equal to causation. In the domain of causal inference on observation data, that is Causal AI, the idea is to explore if there are ways to perform some kind of randomization or removal of bias in the historical data programmatically so that we could make causal claims without running controlled experiments. Before we move further, it's also very important to also understand the concept of ignorability assumption in causal inference. In the earlier example of a controlled trial with cohort A and cohort B, after proper randomization, we could have picked any cohort for treatment and any cohort for control. This shouldn't have changed the final inference. Later, when we try to make causal inference from observational data, we should also see if ignorability assumption can be held true. There is a long and ever-growing list of algorithms for causal inference in the causal AI space, both for causal discovery and for causal impact assessment. For the purpose of this series, we will restrict our discussion to structural causal modeling and how it can be successfully applied in the context of marketing mix modeling. To understand the relevance of structural causal modeling, let us first look at the practical limitations of traditional ML approaches such as regression. There are four important limitations or assumptions implied in the approach of regression modeling that we will discuss in depth here. These are assumptions of independence, assumptions of identical distribution, overfitting of the models, and assumptions of linearity. The first two limitations are related to what is known as the IID assumption. We touched upon IID assumption in an earlier video. To keep the concept simple and accessible, we didn't spend a lot of time properly stating this assumption. But here we go. In the context of machine learning models, IID refers to the assumption that the training data used to build a model are independently and randomly sampled from the same underlying distribution. Each data point is assumed to be independent of others and follows the same distributional characteristics. This assumption enables the application of powerful statistical methods and learning algorithms that rely on the absence of systematic dependencies or biases within the data. So let us expand on both of these. Independence. The independence assumption implies that the occurrence of a value of one data point does not provide any information about the occurrence or of the value of another data point. It assumes that the data points are not influenced by each other and that there is no hidden structure of correlation among them. Violations of this assumption can lead to biased or unreliable model predictions. This assumption clearly does not hold true in the case of marketing measurements. Your bottom of the funnel, branded and non-branded search is partly driven by the success of your top of the funnel spend. Marketers tend to overspend in certain seasons. That is, your top of the funnel spend in itself is influenced by seasonality. These complex interactions between your input variables violate the assumptions of independence. Identical distribution. The identical distribution assumption assumes that the data points are drawn from the same underlying distribution. It implies that the statistical properties such as mean, variance, and other distributional characteristics remain consistent across the entire dataset. Deviations from this assumption can introduce sampling bias, causing models to generalize poorly to new unseen data. This again is not true in the context of marketing data. Marketers tend to intervene with their spend variables by going dark at times or scaling the spend significantly at times, essentially changing the distribution very often. A model built on the assumption of identical distribution cannot support you with predictive accuracy or, most importantly, in performing robust what-if scenario planning. Model overfitting is the third limitation. Real-world marketing needs to be modeled against a lot of input variables. Too many variables with few observations could lead to high p-value, high confidence interval ranges, and overfit models. Overfit models tend to memorize more and learn less. These models show a good fit on training data, but cannot predict or fit well on the future data. The last limitation of regression-based approach is the assumption of linearity. Regression approaches applied in most of the MMM modeling cases assume linear relationships between the input variables and the target variable. This is very far away from the reality in which marketing operates. In MMM, as the variables are non-linearly transformed via Acyclic and saturation transformation, the data point itself becomes non-linear. Though this addresses the issue to some degree, this is more of a hack and not a very robust approach. Recently, a paper from Yoshua Bengio, a famous deep learning researcher, characterizes the limits of deep learning and lays out an agenda for causal machine learning research. The paper argues that the core problem is that the characteristics of the data where you apply the algorithm often drift away from that of the data where you train the algorithm. You get cases of self-driving car algorithms making mistakes a human could easily avoid, despite being trained on millions of miles of road data. For a deeper understanding of IID and the impact of this assumption on the outcomes from traditional machine learning algorithms, refer to this blog by Robert Ness, who is a thought leader in the space of causal AI and also has authored a very popular book on the subject. In an earlier video, we did mention that reality needs to be thought of as a graph or a network with edges and relationships. Reality is not tabular. Take a look at this tabular data here. When this is passed to a regression-based approach, the graphical form of this will look something like this. Here, there are a bunch of variables such as seasonality, brand equity, demand generation, demand capture, etc., all of which are shown as independent to one another with no interaction between them, linearly driving revenue. In a graphical world, reality is quite different. It looks like this. Here, seasonality drives revenue and also some spend decisions. Some of the spend variables, such as demand generation, drives other spend variables, such as demand capture. Brand equity is the result of demand generation, while brand equity also drives some baseline revenue. Let us not worry ourselves with the structure of the specific DAG here at this point, but let us be very clear that data in itself won't have the context or the knowledge to suggest the causal structure. Causal structure needs to come from someone who understands the business and the domain. That is, AI needs humans. Here, again, the nature of the flow of information from the input variables or the causes to the target variable or the effect could happen across different types of causal data structures or causal paths. Three of these structures from the perspective of the causal DAG are the mediators, the colliders, and the confounders. Seasonality is a confounder here, as it drives revenue and top of the funnel spend. Demand capture and brand equity are the mediators. To make proper causal inference, that is to remove the bias, one should condition on confounders and mediators. One need not worry about colliders, as those are closed paths and do not allow information flows. This process of conditioning on confounders and mediators is the process of creating graphical independence between those variables. Let us look back into the case of Simpson's paradox that we discussed in an earlier video. Here, your inference depends on whether you ask the question at the population level or at the job level. At the population level, women are underpaid, but at job levels, they are overpaid. You intuitively know that asking the question at the population level seems to be correct because that aligns with your wisdom that women are generally underpaid compared to men. Now, if you generalize this logic and decide to always infer at the population level, you will get into some trouble very soon. Look at the second table. This is a dummy data where the variable names are changed from female and male to healthy and unhealthy. Here, if we apply the logic of inferring at the population level, you will get some counterintuitive results. That is, an unhealthy lifestyle pays more. We can decide to condition on job type or not only once we understand the true meaning of male or female and healthy or unhealthy. Let us create DAGs for these two cases. This is the DAG for the first scenario. Gender is the confounder here. Gender decides your chances of getting a particular type of job and your salary. Hence, the decision to condition the analysis should be at the gender level, which in this case is the population level. However, in the second example, job type decides whether your lifestyle is healthy and your salary band. Hence, the analysis should condition on the job type, which suggests that healthy lifestyle is more rewarding. In the above exercises, we were conditioning on the confounders. Similarly, if mediators were present, we should also condition on the mediators. This approach is known as blocking of the backdoor paths in the structural causal modeling parlance. This is done so as to achieve graphical independence between the causes. This graphical independence also can be interpreted as statistical independence. And this is the biggest contribution from Judea, who authored the book of Why that popularized the idea of causal inference and kickstarted the field of causal AI. His approach is also called the Judean framework of causal inference. This framework has offered a way of interpreting graphical mathematical independence as statistical independence based on causal Markov condition. He received the Turing Award in year 2011 for his work in structural causal modeling. He devised the method of do calculus, which could be used to learn causal impact when ignorability assumptions hold. Remember the ignorability assumption that we stated earlier in relation to the controlled trial of medicine. In causal inference on observational data, the ignorability assumption is hard to find. However, one can look for conditional ignorability. The conditional ignorability assumption, also known as unconfoundedness or conditional exchangeability, posits that after controlling for a set of observed covariates, the treatment assignment is independent of potential outcomes. Structural causal modeling is a very promising framework. However, there are a lot of challenges in adopting this as a standalone approach for marketing mix modeling. Lifesight's innovation in the space has been to adopt a hybrid of regression-based approach and causal modeling to provide a robust measurement technique. Regression approach is used for time series decomposition of seasonality and trend, find the best fit for various Hatzberg and saturation transformations, and then to pass these transformed inputs to a structural causal model for causal discovery and causal impact estimation. This way, we are able to leverage the best of both worlds, the time-tested approach of regression with the emerging approach of causal AI. Regression is able to better handle transformations and incorporate temporal nature of marketing data, while structural causal models can complement regression with more robust effect estimation and coefficients. The main challenge in causal AI is the presence of invisible confounding variables. We are unable to control for all the confounders or even factor in all the confounders in the analysis. This could add bias that's unknown to us. This is where experiments continue to play a key role. In experiments that are properly designed and deployed, we can manage better randomization and control to a larger extent than in observational studies. We will talk more about the concepts of incrementality experiments and the steps in designing and deploying powerful tests in future videos.